Hello everyone, welcome to the presentation of our collaborative work on evaluating the performance and the potential benefits of building scale CHP systems based on the RESHeat technology. The technology has the potential to simultaneously reduce greenhouse gas emissions and increase the energy security of the inhabitants while providing some opportunity for income generation. The current research focuses on the use of distributed electricity storage at several scales and its contribution to achieving those benefits. Let us start from the proper context. The greenhouse gas emissions have grown continuously for the last century, with small exceptions related to reduced economic activity, and the latest such episodes were during the COVID-19 lockdowns. Consider the electricity generation potential for a family house in Poland fitted with a small photovoltaic panel array. The chart shows the typical pattern of solar irradiation for the area over the span of 1 year. It shows a visible peak in the summer and a low generation in the winter, with typical values shown at the bottom of the slide. The RESHeat project has defined the general topology shown in this diagram. It includes photovoltaic panels, solar thermal collectors and photovoltaic thermal collectors. The system is equipped with the relevant electrical controllers and heat pumps. Currently, it only applies heat storage. The higher temperature fluid from the solar thermal collectors is directed to an insulated tank for current use of hot water, while the output fluid from the photovoltaic thermal collectors is sent to an underground tank in touch with the ground, which is not insulated, and this is used for using excess heat in the summer for ground heat regeneration. The system demonstration sites were first evaluated and are currently at the stage of experimental operation with data recording. The expected performance is to cover at least 90% of the building energy demand with the demonstrated facilities. It is interesting to evaluate if it is possible to extract more from such a system. What about storing excess electricity seasonally, in addition to the local buffering batteries? In this case, a key question is whether physical electricity storage is possible in competition with the virtual storage of first exporting and then importing power from and to the central electricity grid. The energy flows implementing such an idea are illustrated in this diagram. The red arrows here illustrate the heat flows, and the blue arrows denote cooling, and the green arrows denote the power flows. The conceptual diagram essentially adds the electricity storage link to the description. The most important factors to consider are the round-trip efficiency, the energy density, capacity, and the possible scale. Cost is also a key consideration, and of course the service life is an important constraint. In this sense, the nowadays pervasive lithium-ion batteries feature a relatively short lifespan, which potentially means high costs and emissions on a life cycle basis. Energy storage technologies can be classified by their principle of operation, as illustrated on the slide. The most pervasive and proven from them are pumped hydrogen batteries using hydrogen as an energy carrier and storage option is under intensive research. However, there are still serious issues with the achievable storage densities, round-trip efficiency and safety. All these options have been included in the evaluation. Moving to the case study, you can see the house demo site in the photo. The data for electricity generation and electricity demands are shown. The seasonal variations in the generation are well pronounced, while the demand variations are smaller, keeping the level in the vicinity of the 2000 kilowatt hours monthly. This is a summary of the formulated optimization model. The solar energy input is modeled accounting for the variability. The house's electricity system is connected to both the grid and the external storage facility. The overall objective is to minimize the annualized cost of electricity. On the right-hand side, visualize the decision variables, the constraints, and the main approaches to reduce the costs. In terms of equations, this is the structure of the model with the total annualized cost objective function, the constraints, and the decision variables. The life cycle scope is applied to emission and cost evaluation. This slide shows the equations for the life cycle cost. The main cost components are illustrated in a tree classification, with the main categories formulated as capital, operation and maintenance, and fuel costs. The environmental assessment part takes the greenhouse gas footprint as a criterion. Of course, other footprints and criteria can be added in the further model elaboration. The following cost performance parameters were used in the optimization concerning the considered electricity storage options. Similarly, the greenhouse gas emission performance was estimated and specified as parameters in the model. The system design and operation were optimized, and this slide shows the results for a grid electricity price of 40 euros per kilowatt hour. Note, the price levels are consistent with literature data published in 2022, which actually lag the real economic situation. So the lime green series here, it represents the electricity demand. The results indicate that the need to import some power from the grid in January and February, here with the blue bars, and then with some storage charging from March until October, which is the purple part of the bars, and then in November and December some of the stored electricity is used, which is here, and all these months under some amount of photovoltaic electricity generation. If we consider a grid electricity price of 80 euros per megawatt hour, then the photovoltaic array is sized substantially larger, which results in the elimination of all grid import and the need to store electricity externally diminishes to very insignificant levels. Much of the generation of electricity is then sold to the grid. The performance of the optimized design for the two scenarios is summarized in this table. The results indicate that higher electricity price level tends to stimulate both increased sales of power to the grid and the effective reduction of global greenhouse gas emissions, which takes place mainly as a result from substituting fossil-generated electricity. In conclusion, RESHeat technology offers a flexible combined heat and power system architecture. The current design of the system features thermal energy storage and ground heat regeneration. Based on that, this current research is focused on exploring the potential impact of adding external electricity storage to the system beyond the typical local battery pack. The optimized system shows promising results in terms of both economy and emissions at the already very low, outdated grid electricity prices. So what should be done in the future? Firstly, it's important to improve the granularity of the model. This would be one of the ways forward. Then the consideration of different grid prices for export and for import of grid electricity is also a key development. These parameters provide an indication of how much is the virtual storage cost for electricity. The model can also benefit from adding eco-cost explicitly and to add more accurate model features that would allow the evaluation of specific storage technologies in realistic cases. Such examples of such technology, say pumped hydro or energy vault. I would like to acknowledge the funding of the RESHeat project for demonstration of the technology. I would like to spend a couple of minutes to encourage everyone who is interested in further scientific discussions and technology discussions visit our website for this SPIL conference, which will take place in November. If anybody is interested, please contact me. And of course, just a week and a half from SDEVES, we are going to hold conference press in Thessaloniki, the 26th conference on process integration, modeling and optimization for energy saving and pollution reduction. So with this, I would like to thank everyone for the attention. Please use the QR code to obtain my contact details if you're interested for further discussions. I'm looking forward to the discussion live at the venue and in the conference system. Thank you.